So for those that are joining for the first time, the reason we created this is we were very fortunate to attend a number of PFAS conferences across Canada last year, and it was very clear that the market is um, just needing a place where people can go learn right from their desk and not having to pay hundreds or thousands of dollars to learn some of the emerging aspects of PFAS. So we've been very fortunate to connect with colleagues, peers, leaders across the country around PFAS, and we're bringing this one to you again, coast to coast. We've got anybody joining from Victoria all the way to PEI, so it's just remarkable. Just a quick introduction on our end. BV has been doing PFAS analysis for well over 10 years at our laboratory. We were one of the first to get accreditation within Canada as well as the US. So Andrew takes care of all of our PFAS related work and is our market leader in that in Canada. And Stephanie manages our portfolio out in the US. And I have direct oversight over both of them, as well as our Western Canadian geography. It's an investment that we continue to make significant strides in. And I'll pass it over to Andrew to just do a quick intro on kind of some of the updates we've made within our PFAS laboratory, some exciting updates, and then we'll throw it over to Michael.
Yeah, thanks, Josh, and good morning, good afternoon to everybody. In previous versions of this, we mentioned lots of things that were coming, so it's exciting to confirm on this month's installment that we do have 2 brand new instruments that are up and operational, along with 6 automated extraction units, and this is really added to our PFAS capacity and capabilities for this year that we're much more easily able to churn through the volumes, and we turnaround times has been very consistent of late, and we haven't had any backlogs, which was a story that we were telling last year. And the other great piece of news that we have, our operations team has been working very hard the first half of this year on a method improvement and optimization, and what they've been able to do is combine all the 3 recognized methods, the EPA 1633, 533, and 537, and make available the from each of those runs in one single scan. So it allows us to run your sample once, and we can capture up to 47 parameters. And this will be reported at a low level detection limit for both waters and soils. So instead of trying to match various methods to regulations before, and it can be very confusing, we've simplified the process. You can simply request PFAS scan, and we can report up to 47 parameters and turn on or turn off the ones that you want. It is accredited with SEC, and we're hoping that it makes PFAS analysis for our customers much easier going forward. And we're looking to implement this on August 1st. So I'll pass it over to Michael. He's comes to us from Arcadis. I think it's been 10 years, is that right? In the market space for PFAS, and has a great almost
yeah.
And is going to share with us some of his knowledge on your investigation, PFAS investigation, and the remediation techniques being used on some of those sites. And I really look forward to hearing about this. I think it's a key piece of the marketplace right now, that there's a lot of different options, and I think trying to choose the best one for site can be challenging. So I think this will be a great informative session. So I'll stop sharing and pass it over to you.
Great. Okay. Thank you both for the introduction and for having me here. I think this is a great opportunity as well. My understanding is that people of all experience levels have been joining this webinar series so far, right? And that's great. So I tried to tailor this presentation to meet the needs of everybody, right? It's going to be high level. There's a lot in here, but I didn't go too much into the details. There wouldn't be enough time to if I wanted to. But yeah, and I just appreciate these webinars, right? I agree the word needs to get out, and these are the platforms to do it. Nice, free as we said, and yeah, so very happy to be here. Thanks for having me. Just a little bit more about myself. So as Andrew said, I do lead Arcadis Canada's PFAS services team here. And Arcadis Canada is not a small company. We're about 2,700 people, but it's Arcadis Global that are real leaders in the investigation and remediation of PFAS. And in fact, we have a wealth of technical experts that work closely with universities, government agencies, and remedial vendors to develop, research, and advance a lot of these technologies that we're going to go through here today. Okay, so just confirming that I'm sharing the right screen and you guys can hear me.
Yes, looks
Good.
great.
Okay, so the presentation, it looks something like this, right? I do have to do a little bit of background. It's not going to be what is PFAS. I know Andrew did a great job on the first webinar of that, but it's going to be, why are PFAS different and how does that affect our remedial technologies, right? And what are the influential chemistry that we can use? I want to talk a little bit about the mechanisms of destruction because I think that's important. Then we could dive into treatment technologies for liquid, and I'm going to separate that out by the mechanism of treatment, right? Is it absorption, separation, or is it actual destruction? Then we can move on to treatment technologies for soil, and again, the mechanism, absorption, fixation, destruction. And if there's time, I'd like to talk a little bit about aqueous film forming foam transition, right? And this applies to anyone who has large fire suppression systems, such as airports or industrial facilities that currently have AFFF on site. This is being phased out. Eventually, we're going to need to replace that with a fluorine-free foam. And we've learned that that is not a simple process of getting old foam out, rinse it with water, and put new foam in. And I'll get into the details on that if I can make time for it. Okay, jumping right in. So why are PFAS different? Right, so there's thousands of PFAS compounds, and it depends on what definition you're going by. I've heard 4,000, I've heard 12,000, I've heard more, and I've heard less. For the point of this presentation, we'll just call it thousands. And they have a wide range of molecular weight. Many of them are polar and therefore soluble. They're both oil and water resistant. They have surfactant characteristics depending on chain length. They have negligible relevant volatility. They're thermally resistant, biologically recalcitrant, strongly electronegative due to that carbon-fluorine bond. They form supramolecular structures. Their properties are dependent on chain length, so we have a wide range of different types of properties we can see. They're ubiquitous in the environment. They're found in the environment at parts per trillion levels, which is where those criteria are coming down to, right? So wow, there's a lot here, right? But if we look closely, there are some things here that we've been able to utilize to our advantage as we develop treatment technologies. And I'm talking mostly about what we can do with the longer chain PFAS, who are amphiphilic, right? They're dual phase loving. They have a strong affinity for that air-water interface. And so this bubble that I'm showing here is actually a really great way to separate out long-chain PFAS from water, from drinking water, for example. But if you look down at the graph below it, you'll see that as chain length decreases, solubility increases, and that amphiphilic property also decreases. And so short chain PFAS are not as attracted to the air-water interfaces. And in fact, they're more soluble. However, that high solubility and high miscibility for other solvents that we've been seeing may present other opportunities. And I'm just high level, vaguely familiar with some work being done to try to really target those short chains, those C1, C2s, and C3s. And I'm really hopeful that we'll start seeing some data come from that soon. Like I said, I want to talk about the terms basically of destruction, right? So mineralization is the complete destruction of the PFAS molecule, and your end products are going to be carbon dioxide and inorganic fluorine. Once that happens, PFAS will not reform, right? It took energy to make PFAS. It's going to take energy to break PFAS, and then it would take energy to reform it. I'm going to be saying that quite a bit, I think, during the presentation. Defluorination, on the other hand, is more of an iterative approach where you take a longer chain PFAS and you break it down into a smaller chain PFAS. And a lot of the technologies use that process, and sometimes they can keep carrying that process through down and achieving some mineralization, but as you'll see, a lot of them just create smaller chain PFAS, and in some cases that's the best that we have. A little bit about total oxidizable precursor because it comes up, the top assay, right? This is an analytical procedure that the lab can do on a sample. Why we want to do it is because of what we call the dark matter, the precursors. Like I said, there's thousands of PFAS, but as Andrew was saying, the method 1633 measures about 46 of them. But we know, and I know I said that they don't biodegrade, but some of them do biodegrade. These precursors will break down in the environment naturally, but they become the daughter end products that we are concerned about. And so if we're trying to determine the source mass at a site, if we just use that targeted analysis of method 1633, we're going to end up with, look at the bar down here, this dark orange as a sum of PFAS, for example, right? But if we do a top assay, the lab will run a targeted analysis on a portion of that sample. Then they will subject that sample to an oxidative process using heat and prosulfide and things that I'm not sure if Andrew could explain better. And then once that's completed, then they'll run the targeted analysis again. And this lighter orange bar is an example of what you're going to end up with, right? So order of magnitude more. You're seeing that dark mass now being transformed into the PFAS that we can detect and that we care about, right? So keep an eye out for that. We'll be talking about that a bit more as well. So just some key takeaways on this background section before we get into treatment technologies, right? So PFAS have a complex toxicology, and the cumulative effect of the co-exposures of different PFAS is really not well known, and it's starting to drive those criteria down. PFAS are ubiquitous in the environment at parts per trillion levels. They are impacting drinking water wells, and we're seeing that a lot from the United States right now. We know that conventional water treatment technologies are generally just not going to be working for us, and that's because the biodegradation that those usually employ is simply going to transform those precursors to the perfluoroalkyl acids that we are concerned about. Same for chemical oxidation. PFAS destruction is an energy-intensive process, right? It took energy to make PFAS, and it's going to take energy to break it. So the current state of the practice, because there's no silver bullet right now, is a combination of treatment technologies in a treatment train approach. What we're trying to do here is we're trying to concentrate the PFAS as much as we can and then apply our energy intensive destruction, right? You don't want to spend all that energy and all that cost trying to destroy a dilute waste stream of PFAS. It is not going to be cost effective. So those are the takeaways. So let's talk about treatment technologies for liquid. And so we're going to hang out on this slide for a little while. It's a busy slide. This is a graph. It's showing the treatment technologies, and it's showing them on the x-axis of effectiveness and on the y-axis of stage of development. Now, this is going to be subjective, but this is where Arcadis feels that these technologies currently sit on this graph, right? And I'm sure it's changing all the time. So my plan here is to go through a lot of these, just talking through on this slide at a high level. And then I've chosen a select few with some slides following that. Okay. Oh, we have them separated out by the mechanism of treatment. So absorption, separation, and destruction with the outlines on the box. Okay, so top right, you've got your most effective and commercially available. These are the workhorses that we've been employing for quite a while in Canada and around the world, right? Activated carbon, resin, nanofiltration. These are really good tools for treating PFAS in liquids, and I have a few slides, so I'm not going to get into detail on that yet. Fractionation is an interesting separation technology where we utilize that amphiphilic property to create bubbles and pull that PFAS out of the waste stream. Definitely, I've got a slide on that one as well. Incineration of liquid is something that we've been doing in Canada for a while. We probably all heard the concerns of incomplete combustion and emissions to the atmosphere then following that deposition. I'm going to talk more about incineration when we hit on the soil slide like this, but it really depends on the facility and the processes that they have, right? And if they do have post-treatment of the gas for complete destruction. Okay, SCWO, that's supercritical water oxidation, right? So that leverages the supercritical phase of a water that is reached by increasing the atmosphere and temperature to specific target levels. Got some slides on that. Hydrothermal alkaline, so that's increasing the pH, the temperature, and the pressure, but to below supercritical, so subcritical levels. Then you're creating free radicals then that can attack the PFAS and destroy it via mineralization. Sonolysis, we're talking about sound energy, and that's creating bubbles. And then those sound waves are stretching and releasing those bubbles until they make them burst. It releases a huge amount of energy. I have a slide on that one as well. Plasma, you're putting large amounts of energy into a gas or liquid to create a reactive species like hydroxyl radicals that can then attack the PFAS for destruction. Electrochemical, right? We're applying a current to a media between an electrode and an anode. Same idea here. You're trying to create those reactive species that we know have been shown, at least laboratory and some commercial, to be able to destroy that PFAS via mineralization or defluorination in some cases. Cement kilns, I have a slide for that in the soils portion because it's sort of similar. It's basically incineration, but with a longer residence time and way higher temperatures and with existing infrastructure. These three absorbent type materials here on the bottom, I know that there's a lot of good work being done to optimize absorbent technology, right? To find things that can really take all the different chains of PFAS out of a waste stream. Lots of good work being done. The question is, can these be scaled up and can they be cost effective to make its way to the top right of this graph? And we'll find that out soon enough. Flocculation, we've all heard of flocculation in wastewater treatment. We can use flocculation for PFAS. There are amendments that can be added where coagulation will take place, flocculation, and you're separating out the PFAS for treatment in another way. Injected activating carbon, and this would also apply to, let's say, modified clay. I've seen a lot of this lately in the United States and in Canada. There's some challenges around this, but some good things as well, right? It's going to be tricky to get the dispersion that you need for this absorptive media in the ground where you need it. It's really going to depend on the geology. And the deeper you have to go, the more complicated the geology can be. So you're going to end up with some really tight spaced injection points, and that might be okay. Another factor here is co-contamination, right? PHCs are a big problem here as a co-contaminant. And unfortunately, PHCs are often found as a co-contaminant with PFAS due to the historic nature of the PFAS releases, firefighting training activities, or emergency situations where the fires have to be put out, for example. Really, we think that there's a strike zone for this technology. If you need something quickly done to protect a sensitive receptor like a drinking well, while you're waiting for some longer term solution, something like this could be very effective. So it definitely has a place. Advanced oxidative processes and advanced reductive processes, you can see this is still pretty low on the stage of development. And in fact, we talked a little bit about these in some of those destruction technologies where these reactive species are being created. So we'll just have to see as those advance and how they build this graph all together. For biology, there's very little there, right? But there is something. All I really know of actually is something called the white rot fungus that they've done some studies in a lab. It's been shown to destroy PFAS, but we're talking about in the beaker stage right now. And really, it's unclear how that could be scaled up or what that would look like. But still very interesting. This kind of stuff has to be done. We have to see, what's going to be viable and what is going to end up being, impractical to take any further. Okay, so with that, we can jump into some specific slides in it. I'm going to start with absorption. So I'm calling out the mechanism here, right? So we can keep track of that. Activated carbon, resin, modified clay. Like I said, GAC is the industry standard. It's very good at removing particularly long chain PFAS. It is better in lower concentrations and with compatible geochemistry. They found that bituminous often outcompetes coconut and lignite, and that mesoporous fractures are better than the microporous, and that's just so that there's more space in those fractures for the longer chain PFAS to get in. The great thing about GAC is it can be reactivated, and that makes it more sustainable and cheaper, right? Limitations, of course, are competition with natural organics such as total organic carbon and other things. But pre-treatment can handle this. You can increase the pH, for example. This technology, as many do, has challenges with the shorter chain PFAS. But it can manage the PFAS. Something you can do is increase your empty bed contact time and have more frequent media change outs, really. This graph at the bottom is just giving you an example of the effect that TOC can have. You've got a similar starting concentration of PFOA. You've got a pretty big difference in TOC. You go from more than 100,000 bed volumes before breakthrough to just 25,000. So it can have a significant effect. Resins, so they also effectively remove the longer chain PFAS, but they're also good at being a little selective, so getting some of the shorter chains as well. A lower empty bed contact time is great here at 2 to 5 minutes, because that means that you can have a much smaller footprint with these vessels than you can with the GAC vessels. So a cheaper wastewater building, for example, smaller, less space needed. There are types of resins that can be regenerated and some types of resins that are just a single pass. So you can decide which one you're going to go with, but as I'm going to talk about in a second, regeneration of those is pretty challenging and expensive, right? It requires solvents and brine, and it's a bit complex. So another limitation is it can have a higher capital expense compared to GAC, and it's really tightly packed media, so the pumping costs you do see a noticeable difference, right? There is some sensitivity to some site-specific geochemistry, even though it manages it better than GAC. Modified clay, so this again effectively removes the longer chain PFAS. It could be used with some of the geochemistry that's of concern to others. Can be used in remediation. As I mentioned in that activated carbon injection, you can inject the modified clay as well into your source areas or downgrading areas, or it can be used in water treatment. Again, higher capital expense than GAC. Again, high density can create higher pumping costs. At this time, to my knowledge, there is no regeneration reactivation potential for modified clay. Funnel and gate. So I thought this was interesting, and it is a structure that you can put in the environment in the shallow soils that you access from the ground, from surface level, and you can use any of the previous absorptive medias I just spoke about, right? And those would go into these channels here or wells, right? So the groundwater flow is from left to right. You can do some studies at your site to find out which of those media are best, or you can use a sequence of those media, GAC, resin, clay, right? And you can have a bunch of these gates running parallel to the groundwater flow, and then you can treat the water. And once that media is spent, you just remove that media and replace it with new. So I thought that was interesting and worth a little bit of a shout out. Let's talk about a separation technology, foam fractionation. So this one's pretty interesting, I think, right? Foam fractionation is relying on that amphiphilic property for PFAS to like to hang out at the air-water interface of bubbles, right? And so if you look at the diagram here, you've got your PFAS impacted waste stream coming in. You apply a gas to the bottom, which bubbles up, grabs that PFAS, and it comes up as a foam at the top like this, which is concentrated PFAS, and your treated water can pass through. That's a very simple diagram. I have a more complex one coming up. But as you do this, you can concentrate this down significantly. And this is what we're saying, one of the ways, right? You've got to concentrate first before you try to destroy it. Arcadis has partnered with a company called Evocra, and we're working with ozone. So we're specifically the ones working with ozone. And ozone, we believe, is great because it creates micro nano bubbles, which means more surface area, more bubbles, more stable bubbles, and apparently some oxidation potential as well is coming from that. So here's a little more complicated diagram of the fractionation process, right? So you got your raw water coming into a feed tank, and it goes into a column. You can add a reagent if the site conditions require it. Maybe it's a pH adjustment, an anti-foaming adjustment, or I'm not really sure. A lot of things can go in here. Then you apply your air or ozone, and then you collect all those bubbles as concentrated waste. And if you're using ozone, you have to collect that ozone to destroy it, so it's not released to the atmosphere. But you don't have to have just one column. You could have many columns in series, and some might be air, some might be ozone, depending on how your pilot testing went and what showed was the best results. And of course, in a treatment train approach, you can also add a media polish at the end before you have your final treated water. And why not run that concentrated waste through fractionation one more time to make it even more concentrated, right? The less material that you have to deal with, the better. This is kind of what it looks like. You're going to have to do bench scale testing for this sort of thing. Then you do pilot scale testing, and then the full scale system on the right. And you can see those columns hanging out at the top of the can. Destruction technologies for water, supercritical water oxidation. So like I said, SQO, that's what they call it. SQO leverages the supercritical phase of water that's achieved by increasing temperature in water. So the temperature has to hit 374 degrees, pressure 218 atmospheres. At this phase, oxygen becomes fully soluble, resulting in rapid and complete oxidation of organics. And when we're talking about PFAS, that means mineralization of PFAS into the organic fluoride. This is something that's showing a lot of promise with this technology. It's applicable to a wide variety of waste streams. As you can see on the bottom there, we're talking about sludges, biosolids, animal manure, food waste, refinery waste, pharmaceuticals, the media, the ion exchange media, carbon, and even concentrated AFFF, right? They have a saying that I keep hearing, if you can pump it, you can SQO it. And so, in some cases, maybe a biosludge might need a little bit of water added to it, but generally there's not much the type of system like this can't handle. It does have the ability to destroy those shorter chain PFAS that are more difficult to get at, so that's huge. It has a rapid reaction time, 2 to 10 seconds. Doesn't seem to be producing harmful byproducts. That's always a good thing. Some disadvantages, of course, high energy requirements, sensitivity to salts, potential for system corrosion. It does take a high level of expertise to operate and maintain a system like this. It's a complex system, and it's going to have a high capital cost. Senolysis, right? So this is where we said you apply a sound energy to a liquid, and you're creating these bubbles, and through compression and relaxation, you're manipulating those bubbles to expand and contract. And at the same time, the PFAS have the affinity to that air-water interface, so they're being attracted to it, and then the bubble collapses. And when that bubble collapses, it's a huge amount of energy in the form of heat being released at around 5,000 Kelvin. So you're getting mineralization that way. So it's a good destructive technology in that sense. Here's just a couple visualizations to see it could be applied ex situ or in situ. So this cartoon is showing an in situ in a horizontal drinking water well. I know that Arcadis is working with an ESTCP project in the States on this work. It's a promising technology. I'd like to see where this one's going to go. Plasma. So large amounts of energy into gas or liquid, right? Here again, you're creating those free radicals, hydroxyl radicals, to break down the PFAS. This is a defluorination destruction, right? And you can actually see that here on the graph, right? So this graph is showing removal efficiency. So 0 is in the middle, 100 on top, negative 100. So anything above the 0, you've removed, right? So it does a good job at the long chain PFAS. However, if you check here, you've formed some shorter chain PFAS in this process and some precursors as well. So the defluorination process, this is what can happen. There's certainly ways of managing this, longer contact times, keep running it, but it's something that needs to be watched for. This right now is still um, in the bench scale phase mostly. I think they're building a container that they can take to sites for some pilot testing. The flow rates are going to be pretty low at 2 gallons per minute at this time, and some fairly high energy rates as well. Okay, so we're moving on to soil now. So these are PFAS treatment technologies for soil. We've got the same graph looking thing, right? The same effectiveness on the x-axis, the same stage of development, the same subjectivity that I mentioned. Going through this again at a high level and then hitting on some of the slides in more detail. So starting at the top there, landfilling and engineered containment. These two are definitely used in Canada quite a bit, right? Landfilling, we do have landfills in Canada that currently accept PFAS impacted soils. Obviously, the problem here is it's not overly sustainable or cost effective to be trucking our soils across the provinces and country. Space is an issue. There's some concerns that we're just moving a problem from one area to another. But this is, at this time, one of the better options that we have. And it also depends on how that landfill was designed. Does it have leachate collection system or not? So then engineer containment, I believe this is mostly going to be talking about soil containment cells. So a lot of site operators will excavate out a source zone, the highest impact PFAS. Let's say it's from a firefighting training area on a military base, for example, and they will put it into engineered containment cells where it can't be accessed by surface water and it's not leaching into the environment. And it's just there, and it's there waiting for technology to improve and cost to come down. We have quite a few of these across Canada. As long as they're designed well and monitored well, because they do degrade over time, this is an option if you have the space on your site while we wait for these technologies to improve. Soil washing and soil stabilization. I've got slides that are going to talk about those together, so I'll leave that. High temperature incineration. So again, this is something that we use in Canada often. It is a good technology. There are the concerns that we're not getting full combustion. There's air emissions, right? For this, you have to be reaching temperatures of approximately 1,000 to 1,400 degrees Celsius for a 2-second resident time. It's easier to do that with soils than it is for a liquid stream for sure. It's gonna be pretty energy intensive. You got to truck the soils there. It's probably not going to handle tons and tons of soil, but certainly for like source areas and investigative derived waste, it does make sense. Now, I mentioned this. Clean Harbors has done studies to try to show mass balances of what's going in and what's coming out to help fill the data gaps where the concerns are of PFAS being emitted to the atmosphere. I think that generally those were well accepted and have helped to alleviate some of the concerns, but always more data is needed, and it depends on how the specific incinerator is operated. Cement kilns, I'll show a slide on that one. Thermal desorption is an interesting one. So this is not a destructive technology exactly, even though it's shown in the orange. What it is you're heating these soils up to the temperature around 350 to 450 degrees for days to weeks. And what you're doing is you're volatilizing the PFAS into a gas stream, and then you're capturing it into a filtration or an absorptive media like a vapor phase GAC. And then you're going to be destroying that, or perhaps it goes to landfill. So thermal desorption, that's not commercially available yet. A lot of work needs to be done to understand if all of those vapor, all the vapor that's being produced are being captured and there's no emissions. But interesting to see where that one's going to go. Smoldering is an exothermic oxidative reaction, and the idea here is it's self-sustained, so it's going to be a lot less excuse me, energy intensive. This would rely on co-contamination as a fuel inside to keep that burning. But as we know, PFAS on its own doesn't support combustion. However, PFAS, as I said, is often found with PHC impacts. So if there's enough of those impacts, perhaps that could work for smoldering. Otherwise, you're going to need a surrogate fuel to be added to aid in that process. I have heard of spent GAC being used as a fuel surrogate, and I didn't hear this part specifically, but in my mind I went, well, if we're using spent GAC that treated PFAS impacted water as a fuel surrogate to treat PFAS impacted soils, well, that would be awesome. And so I hope they're doing that. I hope they're testing that, right? Ball milling. Ball milling is high energy mechanical collisions to initiate oxidative and reductive reactions that do destroy PFAS, but via defluorination. And this has mostly just been tested in the lab area. There's not a lot of data on the emissions, what's being emitted, and how much destruction we're seeing, if there is any mineralization or if it's all just creating shorter chain PFAS. E-beam. This one is high energy electron beam, so compacted electron accelerators to irradiate soils with high energy electrons. It sounds pretty modern and fancy, but actually this has been used in the pharmaceutical industry this has been used in the medical industry to clean instrumentation, and it's been used for food pasteurization. This has just been done in the laboratory. We don't expect this to handle huge amounts of soil when it becomes more commercially available. I think the thought process here is you're going to have a conveyor belt type of system in a sea can that moves soil along through this electron beam for treatment and destruction. Okay, so let's talk about soil leaching and flushing. This can be done in situ or ex situ. Let's think of it more as in situ for this example. So you have a source area in situ, it's shallow, maybe down a couple meters. You can add water to the surface of those soils, and perhaps with an amendment if you choose, and let gravity take that water down through the impacted soils. And you're going to be increasing your soil pore volume exchanges and removing some of that PFAS mass out into the water. And then, of course, if it's in situ, you're going to need a pumping well to collect that water back up again for treatment in some way. Phytoremediation, we've all heard of this, no doubt, for other contaminants. We do know that plants uptake PFAS. We've definitely seen that data. It's been of concern to us as we look at bioaccumulation and humans, for example. So this is an option. It has some promise here, but it has to make sense, right? You have to have the right type of plants. The hardy plants that will grow has to be more shallow soil impacts, and of course, you still have to deal with that plant material afterward, and that's likely going to be dealt with via incineration or landfilling or soil containment zone. Biodegradation, again, I think the only thing I'm aware of is the white rot fungus. So I hope they're doing good work over there. Okay, so we can get into a little bit more details for some separation. So soil washing is an interesting one, and this is a volume reduction technology. So it's meant to be ex situ, but it can be done on your site or transporting it to a facility that where this exists, this type of equipment exists. And it's about physical separation via attrition scrubbing using desorption to remove the contaminants from the soil into the process water. And then that process water, it would be treated on site and then recycled for further use in the system. What you end up with is you're separating out your coarse material, your gravels and your sands, which have been treated and are good to be put back in the ground, for example. But this process doesn't really get at the fines and the organics very well. So then what you've done is you've taken perhaps a large amount of soil that needed to be treated, and now you just have to treat a smaller amount. So it's more cost effective, take it to the incinerator, the landfill. Yeah, I think that's everything I was going to say there, but I have another slide. This is mostly just for the picture, so you can see what a full-scale system looks like. This was taken from a project we did in Eielson Air Force Base in Alaska. So you can see the water treatment area, you can see the feedstocks, the soil mixing attrition, and then you see the filter press to for those fines to dewater them and make sure that all the water's out and been treated. Now, Arcadis is working with our partner TUQ4, who is based out of Ontario, actually, to ramp up this process in a process they're calling soil washing 2.0. This is pretty new, but what I do know about this is that they are increasing the kinetic energy about 100 times compared to 1.0, and they're utilizing reagents to overcome the kinetic limitations. And the goal here is to just very much minimize those organics and fines that need to be taken off site. So much of those are meant to be treated during this process as well. Okay, fixation, soil stabilization, and solidification. So just a quick definition here. So solidification is the process where waste is encapsulated by a binding agent, such as Portland cement, for example, to form a low permeability solid. This will help restrict contaminant mobility, reduces surface water infiltration to those impacted soils that are bound up, and it reduces the surface area exposed to leaching into the groundwater. Stabilization, on the other hand, is a process where waste reacts with a chemical amendment to reduce the leachability. And that reduces contaminant solubility, toxicity, and mobility. So these can be used together, and they are. And so thinking about it, you've got a source site that's, let's say it's a firefighter training area. You can dig up, add all the amendment, the stabilizing, the cement at certain ratios and some water. You mix it all together and you create a monolith. And between the amendment that binds to the PFAS and the Portland cement that encapsulate the whole thing into a monolith, you've effectively cut off the contamination from the environment, so it won't be leaching as much to the groundwater. Advantages, it's relatively quick to implement. It can be done in situ or ex situ in piles. Good sustainability because it minimizes transportation and disposal, conserves landfill, no backfill. There is some soil bulking disadvantages, right? You're adding cement, you're adding amendment, you're adding water. You're going to end up with a little bit extra soil than you thought maybe, or than you would expect, not thinking about it, right? So you can either have that mound up and the monolith being slightly proud, or you might have some additional soils that need to be managed in another way. Another disadvantage is it does require a proof of concept. So this type of thing is going to start at the bench scale. So I was out at a site myself collecting bucket after bucket of soil that I then had to carry to Purelator to be shipped to a lab where they did various testings to try to determine what are the best percentages of the amendment versus the Portland cement to be used to get the best strength monolith. So there's a process that needs to be done, and then pilot scale testing is recommended. And based on the size of the pit that we're seeing in this picture, this looks like a pilot test being done. It can be done shallow and deep as well, depending on the mechanical equipment that you have. Another graph from the sustainability analysis. Actually, I think this is the first graph I'm showing. Arcadis did a sustainability analysis right on a few of these technologies. I don't have the details of exactly what that entailed. However, just quick glance compared to incineration here, where soil washing, landfilling, and soil stabilizing falls into place. Okay, destructive technologies. So yeah, this is the only slide I have for this. Cement kiln, right? So like I said, these are already existing infrastructures. They have really hot temperatures, 1450 to 1800 degrees Celsius, which is more than the incinerators need for PFAS mineralization, which is 1400, I believe, max. The residence time, 17 to 21 seconds, which is more than the 2 seconds at the incinerators. Disadvantages is you're not going to be managing tons of soil this way, right? It's going to be drums of soil per day. And It's also a challenge to convince the owners of these facilities to come help us take on PFAS waste remediation, right? I think at a time like this, people might be sensitive to bringing any PFAS on their site, even if the science supports it. Okay, so that is it for the PFAS treatment of liquids and solids. Do I have another 5 or 10 minutes, Andrew?
Yeah, we're good for time.
Excellent. Okay. So I wanted to talk about foam transition. Here I'm showing a ARF, a aircraft rescue firefighting vehicle, and some large fire suppression tanks that likely held AFFF at one point, right? And the idea here, as I mentioned before, is that AFFF is being phased out, and fluorine-free foams are being brought in to replace them, so that they're not going to have fluorine. But the problem is that we know PFAS forms structures and aggregates onto the surfaces of these pipes. It forms coatings. And over time, those thicken up, and they do not come out easy, right? They don't come out with water rinses, we're finding. Arcadis, in a project with ESTCP, took some pipes that had been part of a fire suppression system. They cut them up, they exposed them to methanol extractions, and we used scanning electron microscopy to visualize that even after 2 methanol extractions, PFAS are still remaining on the inside of these pipes, right? We knew we had a problem when we looked at this data. So I don't know where this site was. I don't think we were involved in it, but somebody transitioned on their own from AFFF to fluorine-free foam, is my knowledge here. And they did it using just 2 water rinses. So they emptied the old AFFF out. They rinsed their system thoroughly with 2 rinses of water. They disposed of that water as PFAS impacted waste. And then they sampled the fluorine-free foam approximately 1 year later. And this is a top assay analysis. And they sampled at 4 different points. And as you can see, they have very high levels, micrograms per liter levels of PFAS mass in that fluorine foam that they're now, discharging to the environment every time they do a training exercise or deal with an emergency. Arcadis, back a few years ago now in Australia, developed a organic biological uh, solvent that can help get that hard to reach PFAS out of there. We call it fluorofighter. And again, on an ESTCP project, they took pipe pieces and they had a process. They rinsed it all with either methanol, water, or fluorofighter, and then they sampled the rinsate from that. And as you can see, our fluorofighter outperformed methanol and tap water significantly at 2.5 times for water and 1.9 times for methanol. So Arcadis has developed this approach to foam transition, right? The first step is you have to choose a replacement foam. There's quite a few of them out there. They're not made all the same and equally. And you have to understand that the physical nature of these new foams isn't quite the same either. It doesn't behave the same. And that may mean that you have to make modifications to your system to use it. So the impacts on the system operation is the second part of this. Then we conduct a cost benefit analysis, right? Some things don't make sense to go through the cleaning process, and it might make sense just to throw out, like a hose reel, or to dispose of responsibly. I mean, but if you have that large vehicle I talked to you that about the ARF there that's worth hundreds of millions of dollars, yeah, it's going to be worth cleaning that one, or an underground storage tank, for example. Once you determine that, then the system can be planned and the system cleaning can start. Then you do PFAS verification testing and disposal of the waste. So that's a real quick summary of the process. We've done this all over the world, Australia, the US, UK, and we've done it at a few airports in Canada now, including at the Calgary Airport in partnership with the Calgary Airport Authority. We did this in 2023, very successful project that we did where we cleaned 4 of their ARFs And I'll describe the process a little bit. They started, once the AFFF was removed, they started with a post-water rinse, and then they circulated the fluorofighter one time for a period of time. Then they disposed of that. Then they did it two more times, disposed of those, and then a final post-water rinse. After each of those times, they took a sample of that rinsate using three different methods: the targeted method 1633, a total organic fluorine, and a top assay. And here we're just showing the percent removal from the original in these. And as you can see, we've got really good percentage removals. But not only that, but all these analyses are agreeing with each other very well. Definitely a success story. The Calgary Airport Authority has been really pleased with this and has spoken on a few webinars, in fact. Um, yeah, so just wanted to share that success story, and that may very well be my last slide, and it is. So
That was fantastic, Michael. It certainly seems like, PFAS is just such a complex problem that there's not going to be a single silver bullet for any solution, and it definitely seems like it's going to have to be a combo approach for projects on trying to clean it up.
agree totally, right?
Yeah. I don't see any questions in the chat, and we do have 5 spare minutes. But yeah, if there's one audience member want to go ahead, we'll put you on the spot, Michael.
Hi, Michael and Andrew. Hi, how are you?
Good,
Good,
thanks.
thanks.
First of all, I want to just to thank Michael, in fact, for this informative session. It's very clear, especially for me, because I came from a background, I already faced these issues, background of construction faced all these issues. And thank you so much for you to present Arcadis approaches into how to solve, or let us say, solve these issues. So very clear, and thank you so much for you, Michael, and thank you, Andrew, as well. Thank you.
Thank you.
No problem. I'm just sort of thinking, like PFAS it's really not just isolated to environmental problems. It's not your typical site remediation, like that Calgary airport is a great example of yet another PFAS problem folks are going to have to solve. Yeah, so a wide variety of techniques is definitely going to be the answer.
That's right. Then there's the background challenge, right? We're collecting quite a bit of data. Different countries, just data where we don't suspect PFAS, right? In the shallow soils, and yet it's there, right? It's ubiquitous, and that needs to be understood so that we can develop target levels for for the clients, so they're not trying to remediate an impossible levels here, right?
Yeah. So there is a quick question. I don't know if the answer is...
but sorry, Andrew. By the way, I can agree with Michael in this regard, because actually it's sometimes there is a big challenges in this respect. Especially, I worked before on what we called artificial land in Dubai. So we faced a lot of issues and a lot of challenges in this regard. However, it's solved, but again, it is challenges. It was a big challenges, in fact. So again, it's a challenges. These approaches are a challenges. Yes, I can agree with Michael in this regard.
So there is a quick question on the lines of photo remediation in the lab phase and in development. In the lens of a risk assessment, which plants would these include, and would it be significant enough to segregate the plant material for containment purposes?
I know of this treatment technology just at the highest level, but I can speak to it more from my investigative experience, right? Where I've been in these drainage ditches and sampling this plant material, and we targeted the aquatic vegetation that was in the wetted bank of streams, right? Because that is, first of all, the stream is what was transporting the impacts, and it was in the sediment and it was in the surface water. So those are the plant materials that we did see impacts in as we analyzed those in the lab as part of our risk assessment process. Now, what you're asking, however, is which are the best plants to use, and unfortunately, I don't have that information, and I'm not sure that anybody has that information right now.
Yeah, definitely an evolving science, I would think. Well, why don't I leave it there? Thank you, everyone, for joining us. We do have another one booked for next month. I think it is July 17th. And so if those that have registered, we will send a follow-up email with some of the details of this one and a recording. And then you'll have a link for the next one. I believe it's going to be a different take on PFAS, where there's concerns at ski hills from fluorinated waxes. Certainly not an environmental problem folks initially thought of when we're having to deal with PFAS. But so that'll be next month. So thanks again, Michael. Great presentation, great information, and I'm sure if anyone wants to reach out to you, you're open to a call or an email. And yeah, thanks everyone for sharing your lunch hour with us.
Thank you.
Thank you. Thank you so much. Thank you.
Take care, all.
Bye. Thank you.